Thank you for giving me the opportunity to give this talk here today. According to Mandelbrot and Taleb, just 10 trading days represent 63% of the financial returns of the past 50 years. And what this tells us about the financial market is that it is wildly stochastic. There are single events that contribute massively to the overall result of the whole process. And while this is well known to be observable, for example, in financial sciences, but also other fields of research, I would like today to talk about this phenomenon in systems biology. So before we dive into this topic deeper, I would like to classify different types of stochasticity. And I would like to start with mild stochasticity that can generally be modeled very nicely and where the stochastic effects are not that huge. One example of mild stochasticity is a normal random variable that can, for example, model the species count in simple birth-death processes. One interesting thing is that those distributions, those processes, are very much defined by their expected value and their variance. In the Gaussian case, they are completely defined by those first two moments. This changes when we go to systems that are slowly stochastic. One example is the log normal distribution, and different researchers already pointed out that gene expression levels in cells are log normally distributed instead of normally distributed, for example. Interestingly, the moments do not define this process so much. So the expected value and the variance do not constitute so much of the information of this process as you would like it to be. And you can also see this in the sample at the bottom, where you already see that outliers play a significant role compared to the left image, where you have the sample of the Gaussian distribution. One step further, we have wild stochasticity. What you see depicted here is the inverse polynomial distribution, where the probability of observing x is proportional to 1 over x squared. Distributions like this, for example, can be observed in stock markets and many other fields. And the really fascinating thing about them is that they cannot be expected. They do not have an expected value, and they also typically don't have variance or higher order moments. And with this, I would like to, with this unintuitive thing, I would now like to go into this concept of non-existing moments and describe this a bit in more detail. So coming to our biological example, we typically look at number of molecules x. And this is a random variable because we have at different points in time different probabilities of observing our system in different numbers of molecules. So the expected number of molecules at a given time can then be computed as the sum of different contributions. So it could be that we have one molecule with a certain probability, it could be that we have two molecules, and so on, basically till infinity. And what you always see in those summands here are two factors. The first is the number of molecules, which I always think of as the impact of this possibility. The more molecules we have, the higher the impact. On the other hand, you have the probability of being in that state, and they together, they form like a relation. And while for most scenarios, the impact grows quite linearly and the probability decays very fast, such that the high terms here, in fact, are very low, even though their impact is high. There are systems for which the probabilities depicted in red here decay so slowly that actually the growth of the impact, so the growth of this k, is too much to make these terms neglectable here at the end. And with this result, we can see that if the summands do not vanish fast enough here, the overall sum will also not converge. And if the sum does indeed diverge, we do not have a defined expected value anymore. So the question we have now, if we want to build a system that exhibits this kind of wildly stochastic behavior, so if we want to define reactions and propensities that lead to such a system, the question is, how can we model this probability of being in a state? And for this, we use the chemical master equation. It is an ordinary differential equation that exactly returns what we need, namely the probability to observe the system in a certain state at a given time. And in general, the chemical master equation is quite hard to solve, but we'll later also have a look at approximations of the chemical master equations and at how they deal with wildly stochastic systems. So, of course, we do not only have a look at the expected value. The variance and higher order moments can be problematic as well. And similarly, if we have a probability that decays very fast, but an impact that grows, also those can, of course, not be bounded anymore. And one example where indeed all of those moments are non-existent is the inverse polynomial distribution, of which I showed you a sample on the first slide. You see, we have here a probability that has a constant factor 6 divided by pi squared, and then the probability of observing x is basically proportional to 1 over x squared multiplied with that factor. And we will use this fat tail distribution. Fat tail distribution is what I will use as a term for those distributions that do not have all moments. We will use this as the goal of our modeling approach. We want to create a chemical system that leads to a chemical master equation solution of exactly this form. And we use a wonder occurs strategy basically, because first we have a look at where we want to go, then we design a system that is somehow promising to have this solution, and then later we will hopefully see that indeed the system exhibits this kind of behavior, this kind of wild stochasticity that we would like to see. The system we're proposing here consists of 3 reactions. Reaction 1 takes 2 molecules and transforms them into 1. The reaction 2 also takes 2 molecules, has the same propensity, but makes 3 molecules out of those 2. So we have opposing reactions with the same propensities that either decay 1 molecule or grow 1. And in order to have a system that does not extinct our species A, so in order to ensure that species A does not go extinct, we have a slow additive reaction that slowly adds species A to the system. Now, the question, of course, is this really a fat-tailed system? Does this really produce wild stochasticity? If we now simulate this, how does it look like? And therefore, we chose a suitable deterministic initial condition of having 1 molecule at time 0. And then we had a look at the estimation of the chemical master equation solution here. And what you see here are 2 things in this plot. So first of all, you see that this is a log-log plot. So on the x-axis, you have the different numbers of molecules that our system can exhibit. And on the y-axis, you see the probability of having so many molecules. Our reference is the squared inverse polynomial distribution, which is depicted as a black line. And what we would like now to see is that our distribution is heavier tailed, so has higher probabilities for the right end of this distribution. Initially, when we deterministically initiate our system with 1 molecule at time 0, the moments are of course well defined. Our expected value is 1 molecule, and our standard deviation is 0 because we have a deterministic initial value. And therefore, it is not surprising that indeed, for example, after 1 second, you see that this lightest curve here is indeed shaped in a light-tailed way. It is not above the threshold of the inverse quadratic distribution. However, the longer we simulate, the heavier tailed our distribution becomes, and indeed after 5 seconds, which is the darkest of those lines, we see that the slope is basically exactly like the slope of the inverse polynomial distribution, but above it. So it's really heavier tailed than our goal. And in conclusion, as a first conclusion of this talk, we can say that the chemical master equation indeed is capable of describing fat-tailed distributions, and only mass action kinetics are needed to create a corresponding model. So we really did not do anything too artificial. Mass action kinetics into the chemical master equation, and we got a fat-tailed distribution as a solution. Now, I already said that it's quite difficult to solve the chemical master equation directly. Now, the question, of course, is if we have an approximation technique to approximate the solution, how does this cope with wildly stochastic systems? And one of the most interesting approaches here are rate equations, which are basically the expectations of biochemical systems, because we have the expected number of molecules as an ordinary differential equation. And of course, in theory, this should not exist here. So how does this reaction rate equation predict our system? And what you see here on the right is our reaction rate equation that corresponds to our chemical system on the left. And you see the first two reactions do not have any impact because they completely cancel out each other. And only the third reaction leads to a small increase in the expected value. You can also do this for the variance, for example, using Engblom's method of moments. Then you get a bit of a more interesting term. I also depicted both of the lines here on the left-hand side. Please be aware that the y-axis is logarithmically scaled. So you see both of those systems diverge, actually. However, we would expect both of those quantities that should be approximated here, the expected value and the variance, to be non-existent approximately after 2 seconds. And the ordinary differential equations that you see here really do not depict this. They predict some smooth, slowly diverging curves, and this is really not what the system looks like. So as a second intermediate conclusion, we can state that expectations formulated by ordinary differential equations in terms of reaction rates and method of moments are not capable of indicating this wild stochasticity. They predict a completely different behavior. And this is problematic because if you only use those here, then of course you will not see if your system is wildly stochastic or not. So how can we design a diagnostic tool that tells us whether our system is heavy-tailed or fat-tailed or not? And one approach that I would like to highlight here is the stochastic simulation algorithm. It was first published by Gillespie, and it's very intuitive. You initialize your system, you initialize your propensities and your state change vectors, and then until you reached the final simulation time, you repeat 3 steps. You calculate your current propensities, you sample a time increment, and you sample the reaction that will happen next. Then you update your state and your time, and you repeat until you are done. There are many advantages to this algorithm. It is very simple to implement. It draws samples from the true system behavior. So it can really draw samples from the true chemical master equation solution. So there is no approximation of an expected value or a variance here. However, one drawback of it is that the runtime scales with the number of simulated reactions, as you can probably imagine. And now the question is, having this algorithm, can we maybe estimate the expected value and the variance based on samples of this stochastic simulation algorithm? And I depicted the sample-based estimation in comparison to the curves that we already saw for the reaction rate equations and the method of moments here. And what you see is that indeed the orange and the red line, as well as the gray and the blue line in the top or bottom plot respectively, they align very well for the first 2 seconds. So for the first 2 seconds, where we would also expect the moments to exist still, both estimators do a quite nice job of predicting this. However, afterwards it gets a bit different. You see, both lines, the gray one in the bottom plot and the red line in the top plot, they start to diverge from the ordinary differential equation solutions that we have in blue and orange. And this now first indicates that something's wrong in the system. There has to be something wrong, because if I have two estimators for the same thing and they do not agree, then something has to be wrong. And this is our first diagnostic tool. So if you have a look at how your two estimators agree, then you can already have a feeling if there's something that you should pay attention here to. A second thing that I want to point out is one very specific trajectory. At the beginning, I said that in this wildly stochastic processes, single samples or single realizations play a huge role in the overall image. And this is exactly what you see here for that one trajectory, 17,895 out of 25,000. Please keep in mind, this is a log plot. And what you see here is that one single realization reached 50,000 molecules and reacted over 2.5 billion times, while most other samples drawn from the exact same process finished within 30 reactions. And so really the image you see is vastly different. And astonishingly, this one trajectory also aligns very well with the variance estimation that we have of our samples. So this is exactly what I would like to point out. We exactly see this dependency on single samples here in this one process. And with this, I really want to strongly argue that sample-based estimations can indicate whether there's something wrong here. Of course, they still predict something that's not there. They still say, hey, your variance is 2 to the power of 10, while it should not be existent at all. But they indicate that something's wrong. In addition, you can also imagine that if you simulate 2.5 billion reactions, then this takes some time. It took over 2 days to simulate this in comparison to approximately a fraction of a second for most other samples. So we really strongly argue that SSA samples are a very good indication for wild stochasticity in systems biology. In conclusion, we saw that we can build wildly stochastic biochemical systems from simple mass action kinetics, and that the chemical master equation is capable of describing this. From a modeling point of view, this is something very positive. The chemical master equation seems to be flexible, very, very flexible in that respect. However, if you now approximate the solution, for example, using ordinary differential equations that allegedly should approximate those moments, then you are prone to fail with those approaches. And especially both approaches here, the sample-based and the ordinary differential equation-based approach, they both fail in predicting that there are no moments. Still, the ordinary differential equations perform worse in our mindset because they don't tell you that there's something wrong. Last but not least, the stochastic simulation algorithm has the advantage that indeed you see that something is wrong or something is missing for the whole image. So we strongly advise to use this or a few samples of this to check on your stochasticity before you only use reaction rate equations or the method of moments. And with this, I'm at the end of my talk. Thank you very much for your attention.